So in today's video we're going to start chapter 8. Specifically we're going to start with 8.1. All of chapter 8 is about continuous distributions. Most of it's going to be about the normal distribution, which we're going to stick with for pretty much the remainder of this course. But first I want to look through the continuous uniform distribution. It's kind of like the one that we did in discrete. It's just that when we deal with continuous distributions, we tend to describe them slightly differently. Remember, a continuous distribution is something where it can take on any value on the real line, okay? It can be any real value between some value and some other value. So you can say, okay, well, the temperature in a particular country can be anywhere between 0 and 100 degrees, but it can be anywhere on that sliding scale. So we can give it bounds, but it will always be able to take on any value between those two bounds. That's as far as it gets. Whereas with discrete distribution, there are a countable number of outcomes. So it could only be, for example, when we roll a die, the outcomes were only 1, 2, 3, 4, 5, and 6. There were no decimal values, there were no fractional values. It was just those set outcomes. So that is the difference that we've got to deal with here with continuous distribution. So with continuous uniform distribution, and it's going to be the same when we get to the normal distribution, the way that we actually describe these continuous distributions is by something called a probability density function. Okay. But first, let's go ahead and look at what this continuous uniform distribution is. Okay, so exactly the same as in the discrete uniform distribution, every outcome has the same probability, okay, in a sense, in that the probability density function is going to be spread out evenly over some range. So the continuous probability density function, okay, once you've seen this drawn out, it will make a lot more sense. Continuous uniform probability density function. Okay, I'm going to write this function out and then we're going to talk about it, and we're actually going to draw it because it's going to make a lot more sense once you see it drawn out. Okay, what this function does, when you draw this function, okay, we can see that it's going to be 0 everywhere except for between the values of A and B. Okay, and between the values of A and B, depending on what A and B are, it's actually a constant function. Okay, this function does not depend on X. So for example, if this had A is equal to 1 and B is equal to 5, okay, then everywhere between 1 and 5, this function is going to equal 1 over 4. Okay, it's a constant function. So it depends on what your bounds are, but it does not depend on what value you are at between those bounds. So it's a constant function. What this function actually does is when we draw it out, the probability of landing between any 2 points is equal to the area under that graph between those 2 points. Okay, so let's go ahead and draw this out so that you can see it. Okay, if we go ahead and draw it out, okay, we've got our x values here, and if we draw out this function, so we've got f of x, the function value on that y-axis. Let's say that my a value is here and my b value is here. Okay, now drawing out that function, I'll draw it in blue, we know that it is 0 everywhere except for between a and b. Okay, so outside of a and b we don't have to worry about it. The function value f of x is 0. But between a and b, I'll draw it like this as a box. The function value, so so the value that it takes on, is 1 over b minus a. Okay? And it is that same constant value everywhere between a and b. Okay, so it's a straight line. So let's say that I took any two values. Let's say I wanted to figure out the probability that we land somewhere between C and D. Okay? Well, that probability, the way that you figure out probabilities in this case, is to look at the area under the graph between those 2 points. So I would go ahead and figure out the area under the graph between C and D. And that would be the probability that I land somewhere between C and D. Okay? You can't have a probability of equaling a certain point when you are looking at continuous distribution, any continuous distribution. But you can see this with the uniform distribution. The area under a curve or a line or whatever you're looking at for a specific point is 0. Okay? You can't have, let's say I took this value here, we'll call it E. Okay? The area under the graph at E, well, it's just one straight line. Okay? One line under a curve has no area. Okay? You don't have a box drawn. It's just a straight line. So one straight line has no area under a curve. Therefore, for any continuous distribution, you cannot find the probability of that distribution having an outcome equal to something. Okay? But you can find the probability that the outcome will be between two values. Okay? You can think of it in terms of, let's say, temperature. Okay? Let's say that we're looking for the probability that Upland today will have a temperature of exactly 72.3547982 degrees. Okay? You can't do that. It's pretty much impossible to figure out the probability that the temperature equals that particular value on any particular day. But I can say, okay, let's go back and look at historical data. What's the probability that Upland today will be between 60 and 70 degrees? We can figure that out given historical data over, let's say, the last 100 years. We can say, okay, on this particular day, how many of those, like over the last 100 years, on this particular day, how many of those days in the last 100 years landed between 60 and 70 degrees? And we could figure out a probability. But trying to figure out the probability that it will equal a specific value when you're on a continuous line is pretty much impossible. So you can't figure out the probability that an outcome will equal one exact value, but you can figure out the probability that we will be between two values. So that is the case here. It is just the area under the curve between those 2 points, or the area under the line between those 2 points. What you should notice is the area under that line between A and B is equal to 1. Okay? Think of it again in terms of probabilities. The area under the line is the probability that I will land between those 2 points. Now, if I land outside of A and B, my probability of doing that is 0. Okay, I have no chance of landing outside of A and B. But the probability of landing between A and B is exactly 1. Why? Well, let's go ahead and figure out that area under the curve. I erased that X there. Okay, so the area under the curve between A and B. Okay, well, we're looking at the area of literally just this rectangle. Okay, because we are looking at the area under the curve between A and B. Area of a rectangle is going to be the length of it times the width of it, okay? The length of this rectangle, okay, is the distance between A and B, which is B minus A. And then the height, or the width of this rectangle, is 1 over B minus A. The B minus A's cancel, and you just get 1. So we have a 100% chance of falling somewhere between A and B. So this makes sense. Let's say I was looking at the probability of falling between C and D. It would be the area under the curve between C and D. So area under the curve, or the line between C and D. Well, that is just the probability of having an outcome or falling between C and D. Okay, which again is just going to be the area of that grey rectangle, which is going to be C, or D minus C, multiplied by 1 over B minus A. So it's D minus C over B minus A, depending on whatever those values were for this particular problem. So whenever you do any kind of continuous distribution, this is not just for the uniform distribution, but for any continuous distribution, you should find that the probability of landing or having an outcome between two values, so the probability of something happening where your outcome is between two values, that probability is just the area under the curve or the area under the line between those two values. Okay. Now, when we look at the continuous uniform distribution, as I said, it's just you've got this constant function. Okay, that's the particular property of the continuous uniform distribution, is that its probability density function is a constant line. Okay. For the normal distribution, that is not the case. It's actually the bell-shaped curve, and we'll look at the function for that, but most of that's going to be done on the calculator. But the two other things that you need to know about this continuous uniform distribution is its mean and its standard deviation. Okay? The mean, you can kind of figure out why that would be the case. So the mean is like the average value that we would expect to happen. Okay? The standard deviation, you don't need to know where it comes from, just kind of trust me on it. It actually has some calculus involved as to why it is this value. So you don't have to worry about that for this class, but you do need to remember how to calculate them. So this is specifically for the continuous uniform distribution. This only works for the uniform distribution. Okay, the mean is just the lower bound, so the lowest value that this thing can possibly take, plus the largest value that this thing can possibly take, divided by 2. Okay, if you think about it, it's literally going to be this midpoint. Okay, if you do the lowest value plus the highest value and divide it by 2, it's the midpoint. So the mean is always the middle value in this case that this thing can take. The standard deviation is just B minus A, and this is going to look really random, divided by the square root of 12. As I said, you do not need to know where that square root of 12 comes from. It's to do with calculus as to how they figure that out. You just need to remember that that's how you calculate it. In the same way, if that's the standard deviation, the variance, so that standard deviation and variance look at how spread out our outcomes can be. The variance is just the square of this, so it's going to be B minus A squared over 12. It's just the square of the standard deviation. So as I said, don't really worry about where those values come from. The mean, you can kind of figure out why that is. It's the average of the highest and the lowest values. But for the standard deviation and the variance, don't worry about where they come from, but you will need to know how to calculate them. But it's pretty simple. So let's go ahead and do an example of this continuous uniform distribution. So here we've got a fire department that records how long it takes for its trucks to reach the scene of a fire. The distribution of the arrival times of the truck is uniform, so we know it's got its time, so we know it's a continuous distribution, and we know it's the continuous uniform distribution. And it's got a minimum time of 2 minutes and a maximum time of arrival of 15 minutes. So we know that all the trucks will get there in between 2 and 15 minutes. We're going to call X the time it takes for the truck to arrive from the time that it's being called. Okay. First question is, what is the probability that the truck will reach the scene within 5 to 10 minutes? Okay. So if we went and drew this out, I'm going to draw it first just so that we have it before we go ahead and actually calculate anything. Okay, so the minimum amount of time it takes is 2 minutes and the maximum amount of time it takes is 15 minutes. Therefore, we know that our constant function for this continuous uniform distribution would be 1 over b minus a, which is 1 over 15 minus 2, which is 1 over 13. So we can go ahead and draw this out. So we know that the truck will get to the scene anywhere between 2 and 15 minutes. Now the question is, what is the probability of the truck getting there between 5 and 10 minutes? So let's go ahead and draw that out. So we've got 5 minutes here and 10 minutes here. So let's go ahead and draw that. So we want the area under the curve between 5 and 10. That will give us the probability that that truck arrives within 5 to 10 minutes. Okay, so the area under the curve between those 2 points would be, so the area which is equal to the probability. Okay, so the area under the curve between those 2 points is equal to the probability that we land somewhere between those 2 points. So we want the area of that grey rectangle, which is going to be 10 minus 5 multiplied by 1 over 13, which is 5 over 13. So we have a 5 in 13 chance of the truck getting there within 5 to 10 minutes. Our next question is, what is the expected time of arrival of the truck? So on average, what time do we expect it to get there? Okay, well that means that we're looking at the mean time. So we know that the mean is the minimum value plus the maximum value divided by 2. So let's look at our particular problem. Our minimum value is 2. Our maximum value is 15, and we're going to divide that by 2, so that's 17 over 2, which is 8.5 minutes. Remember, our mean has the same units as our actual data. So the expected time of arrival is 8.5 minutes, which makes sense, okay? If it's somewhere between 2 and 15 minutes, 8.5 minutes, which is right down the middle, is your expected time of arrival when you've got a continuous uniform distribution. And the final problem says, what's the standard deviation of the arrival times? This will give us a measurement of how spread out those arrival times are. So I'll use a new page for this. So our standard deviation, okay, remember that was b minus a divided by the square root of 12. So it was our maximum arrival time minus the minimum divided by the square root of 12. Okay. And that, if you work it out, it's going to be 13 divided by the square root of 12, which if you type it into a calculator comes out to roughly 3.753 minutes. Okay, that's to 3 decimal places. So now let's move on to chapter 8.2, where we start looking at the normal distribution. This is just going to be a very simple introduction, and we're going to go into some more calculations next time. But the normal distribution, you have probably seen it before, and it is just a bell-shaped curve. So it looks something like this, which we have looked at before. It looks something like this. It is bell-shaped and it's symmetric. That's the big thing here. It's a symmetric bell curve. And you'll remember when we had one of these symmetric distributions, so this symmetric histogram for your data, whenever you've got this, it means that the mean equals the median equals the mode. So that value is found here. Your mean is right down the middle. It's also the median and it's also the mode. But we tend to call it just the mean, okay, that goes right down the middle. When you have one of these, okay, one of these distributions, so this is representing our data, because it is a continuous distribution, when something takes on the normal distribution, we actually say it can take on any value between negative infinity, which would be this way, and positive infinity, which would be this way. The height of the curve looks at the frequency at that particular value, okay? But you can technically take on any value between negative infinity and positive infinity. But the frequency of it, which is the height of the line compared to the x-axis, is going to get lower and lower and lower. It's never technically going to actually touch the x-axis, giving you a zero frequency. But it's getting less and less and less and less likely as those values get larger and larger or more negative. Okay, so as it gets more and more positive and more negative, you get towards almost a zero frequency. It's just that the curve never technically touches that line to give you an actual zero frequency. Okay, so when you go ahead and do this, you have to take that into account, because technically most of our values won't be that far from the mean. So even though it does go off to negative infinity and positive infinity for this curve, most of your values, as we've seen before with the empirical rule, remember 99.7%, roughly 99.7% of your data lies within 3 standard deviations of the mean. So if we start adding and subtracting standard deviations to the mean, okay, within 3 standard deviations of the mean, so between here and here, so I've just added multiples of the standard deviation to the mean and subtracted multiples of the standard deviation from the mean, I will find that roughly 99.7% of my data lies between those two values, 3 standard deviations below the mean and 3 standard deviations above the mean. So I don't really have to worry too much about what goes on either side of that, where it does tend towards infinity or negative infinity, because most of my data isn't there anyway. So because we are now looking at probabilities, we want to look at the area under the curve. This is a continuous distribution, okay? So the probability of having one certain value, because we are looking on a continuous real line, this x-axis, we are looking on a continuous real line, the probability of getting one exact value that may be some massive decimal is 0, okay? It's pretty much impossible to end up bang on one particular value, okay? But we can look at the probability of landing between 2 values. So in order to do that, we are going to look at the area under the curve between 2 values. So we could look at the probability of landing between here and here, let's say, okay? You are going to look at the probability of landing between 2 values. Now, the probability of landing somewhere under the curve is a definite, okay? You're going to land somewhere. So the area under the whole curve, okay, even past 3 standard deviations away from the mean, the area under the whole curve is 1.0, okay? You've got an area of 1 underneath that whole curve. So let's go back to our empirical rule. We know from the empirical rule that within a fixed number of standard deviations from the mean, the normal distribution contains some fraction of their probability, okay? So within a certain number of standard deviations, I'm going to draw this curve out again just so that we have it, okay? I'm actually going to draw the x-axis of this curve as the number of standard deviations. So my x-axis is going to be the number of standard deviations from the mean. Okay, so that means that at my mean, I'm no standard deviations away from it. Okay, I'm exactly at the mean. Okay, so then either side of that, I can be 1 standard deviation above, 2 standard deviations above, 3 standard deviations above, and I can also be a number of standard deviations below the mean. Okay. Now, let's look at the empirical rule. So we said that within 1 standard deviation of the mean, I have roughly 68% of my data. Okay. So if I look under the curve between 1 standard deviation above and 1 standard deviation below the mean, I know I've got roughly 68% of my data between those two values. That means the probability of landing between 1 standard deviation below the mean and 1 standard deviation above the mean is roughly a 68% chance, a 0.68 probability. In reality, I said it's always roughly 68%. The actual value, the actual area under that curve is 0.6826 to 4 decimal places. So when I say roughly 68%, that is the actual decimal, okay? That means that I can actually split this into 2, and they're going to ask you to do this in your homework. If it asks you, what's the probability of landing between the mean and 1 standard deviation above the mean? So we're looking at the probability of landing between the mean, we'll call it mu, and 1 standard deviation above. Okay, it would also be the same if you were looking at 1 standard deviation below the mean. Okay, the probability of landing between here and here. Well, we know the probability of landing between here and here was a 68% chance, 0.6826. So the probability now of landing between the mean and 1 standard deviation above the mean would be half of that. Okay, which would be 0.3413. Okay, so you're going to have to remember these decimals. I know they're annoying to remember, but you can then figure out to 4 decimal places a probability of landing between the mean and a certain number of standard deviations above or below the mean, because all you would have to do is half that number. Let's look at another situation. So now I'm going to look at the probability of landing within 2 standard deviations of the mean. So if I go 2 standard deviations below the mean and 2 standard deviations above the mean, what is the probability of me landing between these 2 values? Okay. Well, I know that roughly 95% of my data lands within 2 standard deviations of the mean. Okay. So we're looking at roughly 0.95%, or 0.95 probability of landing between -2 and 2. That's a 95% probability. Okay. Now, again, it was roughly. So the area under that curve between -2 and 2, the area under the curve when I go 2 standard deviations above to 2 standard deviations below, the area under this curve here, okay, is going to be the probability of landing between those two values, which comes out to, as I said, it was always roughly 95%. It's actually 0.9544. So now let's say I was looking at the probability of landing between, let's say, the mean and 2 standard deviations below the mean. Okay, what's the probability of that happening? So I'm looking at the probability of being between 2 standard deviations below the mean and the mean itself. So -2 standard deviations and 0, you're at the mean. Okay, what's the probability of landing between this value here and this value here? Well, we know the probability of landing between -2 standard deviations and 2 standard deviations above and below the mean. That is 0.9544. So all I'm going to do is halve that to find the probability of landing between the mean and 2 standard deviations below. So a half of that is 0.4772. Okay. And finally, we said, okay, we're going to look at, in the empirical rule, how much of the data lands between 3 standard deviations above the mean and 3 standard deviations below the mean. Well, we said it was roughly 99.7%, which means that you have a 0.997 chance of landing between 3 standard deviations below the mean and 3 standard deviations above the mean. In reality, as I said, again, it was approximate, to 4 decimal places, the actual probability of landing between 3 standard deviations below the mean and 3 standard deviations above the mean is the area under that curve between those two values is 0.9974. Okay. Now remember, the area under the whole curve is 1. Okay. That's when we shoot it out towards infinity and negative infinity. So if the area under the whole curve is 1, you have a pretty high probability now of landing within 3 standard deviations of the mean, okay? Which means that you only have a tiny probability of landing outside of that in a normal distribution, okay? There is only a tiny, tiny chance of you landing outside of that 3 standard deviations above and below the mean range, okay? So you can do the same thing again. Let's say now we're looking at the probability of landing between the mean, and I'm going to go 3 standard deviations above the mean. Okay. So as I said, landing between 3 standard deviations below and 3 standard deviations above had a probability of 0.9974, roughly a 99.7% chance. So if I now want to find out the probability of landing between the mean, which is here at 0, and 3 standard deviations above, it's going to be a half of that, okay? The area under the curve is a half of that. So it's going to be 1/2 of this 0.9974, which turns out to be 0.4987. Okay. Now, as I said before, whenever we deal with continuous distribution, so whenever something can take on any value along a real line or between 2 certain values along a real line, but it can take on any decimal value, any fractional value between those values, we know it's a continuous distribution and it has a probability density function, exactly as that uniform distribution did. Okay. Now, for a uniform continuous distribution, it had a pretty simple formula, and it was dependent on the lower and upper bounds that this distribution could take on. For a normal probability density function, it is not as simple as it looks, because the remember, the probability density function is the equation of that line, the equation of the curve, and then the probabilities are found by looking at the area under the curve between two values. Okay, so the question is, what is the equation of that curve? What is the equation of this bell-shaped curve that we can then look at the mean and the standard deviations, and we can look at the probability of landing between two certain values under that curve by looking at the area under the curve between those two values. What is the actual formula for that curve? It is a horrible, horrible, horrible formula, but I'm going to write it out just to demonstrate one thing. You do not need to know this formula. You will never use it again, but I want to write it out just so that you can see one thing about it. Okay. That is the formula for that bell-shaped curve. It is a horrible formula, but what we can see from this formula is that it depends on both the mean and the standard deviation. Standard deviation is also here. It depends on the mean and the standard deviation of your data. Okay, so that curve is going to change depending on your mean and your standard deviation. Okay, now if we look at this curve, okay, let's say I drew out for a particular set of data, it followed a normal distribution curve. Okay, so when we did its histogram, we could see it was symmetric and formed this bell-shaped curve. Okay, and that bell-shaped curve had this particular formula. Okay, so we know it follows normal distribution. Depending on the mean, depends on where this curve is going to fall along the real line. Okay, remember your mean is right down the middle. It's also equal to the median and also equal to the mode. So dependent on whatever your data is, that curve is going to shift either down the real line towards the negatives or up the real line towards the larger positive values. So dependent on your mean depends on where this curve is going to go. Okay, if I end up with a larger mean, so let's say now I've got a different set of data, but it still follows that normal distribution, but it now has a mean down here. If it still follows normal distribution, it means that my curve is now going to shift up that real line. Okay, so it still follows that normal distribution, but because it now has a higher mean, I've got to shift that curve. Okay, so that's the first thing to notice, is that the mean basically shows where this normal curve is going to fall on that real line. Okay, it's going to shift it either up or down the real line. So that's what the mean does. What does the standard deviation do? Okay, well, the larger the standard deviation, the flatter this curve is going to be. Remember, just look at within one standard deviation of the mean. Let's come back to this particular diagram. Okay, so if we look at this diagram, we know that if we go one standard deviation either side of the mean, we should have about 68% of our data between those 2 points. We should have a 0.6826 chance of landing between one standard deviation below the mean and one standard deviation above the mean. That means that the area under the curve between those 2 points is 0.6826. Okay. Now, if my standard deviation for a data set is larger, it means that I would still have to have that 68% of my data, that 0.6826 chance of landing between one standard deviation either side of the mean. But if we do that, let's have a look at that. So let's say now one standard deviation either side of the mean fell between here and here. So when I drew my curve, I would still have to make sure that I would have a 0.6826 area under the curve between those 2 points. But now my curve is stretched out. So in order to still have that same area below the curve between those 2 points, my curve would have to be lower. So the larger your standard deviation is, the flatter the curve needs to be. So if we go ahead and draw this again, this time with this larger standard deviation, I would probably end up with something that looks like this, which is much flatter. And now the area under the curve between those 2 points, doesn't look like it in the picture because of a bad sketch, but we would have 68% of our data between those 2 points. The area under the curve between those 2 points would be the same as the area under the curve between those 2 points. Okay, so the larger my standard deviation is, the more I have to flatten out that curve, because if my standard deviation is larger, I've still got to have that same area under the curve between those 2 points, one standard deviation either side of the mean. But if they are further away from the mean, because my standard deviation is larger, it means that my curve has to be flatter in order to make sure I still have that same area under the curve between those 2 points. Okay, so that tells us, let me write this here, the larger the standard deviation, the flatter the curve. Okay, and in the same way as we said before, what the mean does is it moves, it shifts that curve left and right along that x-axis. Okay, so that's how the mean and the standard deviation affect the shape of this bell curve. It will still have that bell curve shape and it will still be symmetric, but the mean and the standard deviation determine where it is on that real line and determine how tall or how flat that curve will be. There is another against all odds video that introduces the normal distribution, and some of it you may not understand quite at this moment, but we will be going through it over the course of the next week, so you'll see more and more of these ideas coming up. But it's a great start to look at that video just so you can kind of see where this is going and what we're going to be doing with normal distribution. If you have any questions, let me know, and I will see you in the next video.